Okay, so as part of the first assignment, we want you to submit your program along with a make file for building your program. And make is a utility that's pretty standard, or make-like utilities are standard, where they specify recipes for building your software. And we'll talk about why this is necessary in a second. So make files are meant to help someone compile and run your code without having to manually type all of the compilation instructions. So there's a special file called makefile that if you place it in the current directory and you type make, the make utility will go and read the rules that are in that makefile and use it to build the software that's in that directory, or build the source code. In the make file itself, the very first rule is used as the default unless you have given make a parameter, a target to build. So if you just type make and hit return, it's going to go into that make file and take the first rule and use that as the recipe to build. If you want to build a specific piece of your code, you can specify a target in the make file and say, I want to make that. And then in the parameter, say make target. Okay? When you see a make file, and I'll show you an example in a second, there's going to be a target, what it depends upon, in the first line, and then a recipe for building it on the second line. So that's basically all make files are a collection of those. Here's a very simple make file. It says I have this target, SD, and this is a binary. See, I want to build this binary. I called my program something, and it's going to build the binary SD. And it relies on this C file. So the code to implement SD is in sd.c. Anytime I make a change to sd.c, whereas this is more recent than the binary SD, then the makefile is going to say, I need to rebuild this thing, right? It checks the modify date and says, okay, this is now out of date. I'm going to make this thing again. And it's going to execute this compilation command that you specify in the second line. And that's what CC in this case is the compiler. I'm going to compile things with these flags, and the output of this compilation, the -o, is the binary SD, and then the source code is sd.c. So target to build, what the target depends upon, and the command that will build it. All right. Here's an example that's a little more complex. So I have, in this case, I have 4 binaries that I want to create. I have SD, which was what you saw before. I have test1, test2, and test3. And I have a target up here that says all. So if I type make, since this is the first line, it's going to make all of these things. Now I could also explicitly say make all, or I could say make test2. And if I just type make test2, it's just going to do this one. If I type make test3, it'll do this one. There's another rule down here at the bottom. It says make clean. And this says there's no target. Always execute this command, and this just removes all the binaries. If you want to clear out all of your binaries, you do a make clean. And this is often used, for example, if you're going to distribute code, and you don't want to distribute all the compiled binaries, because that's sort of big, especially if you statically compiled. Then you would do a make clean, and then you can tar up this thing and send it off. When you submit your programs, do a make clean before sending it to the TA, or uploading it to the Dropbox, because there's no need to upload the binary, because typically we're all running Linux on Ubuntu. She can rebuild the binary from the source that you submit. And one of the things I should mention is that always make sure that you can rebuild your binary with make and run it from scratch before you submit. So we had some issues in the past where it's like, oh, I submitted a binary that works, but then because the make didn't work, the TA couldn't grade it. All right. So subtargets to build in this case, and then a command that always runs in this case when there's no targets. Here's a slightly more complex make file, and you'll see this kind of stuff in production environments where you want to programmatically change, for example, the compiler. So we were using CC in the previous examples. What happens if I got the Intel compiler or I got the GNU compiler and I want to swap out the compiler? I can symbolically set constants to the compiler name, and then from there on out in the recipe I can just use $CC and it'll just swap out the compiler. So all I have to do is change that if I change compilers. Similarly, if I want to specify a certain set of flags to send to the compiler, and I don't want to type those flags every single time there's a compilation line, I can just set the C flags, and so these flags are set using this. If I want to include a certain set of C libraries, so in C, if you're going to use some libraries out of C, you have to link in the specific parts of that library. And so here, I want to use the math library. And I have to append this in the compilation step in order for the compiler to know where to get that code from. So that's this -lm. And so sometimes I'll attach it here. If I want to symbolically say what my targets are, I can say my object files that I'm interested in are these things. And that will specify these as targets for this driver when it compiles. So you see these object files are here, and then to build these object files, they each have individual targets as well. You'll note that these clock.o and clock.c, they don't have build lines. They don't have second lines that say, how do I build these things? There is a default compilation rule that is invoked whenever make sees this and doesn't see a second line. And it basically just does gcc-c clock.c-o clock.o. So you don't have to write that in. It'll default into compiling that. I think that's all. Do you guys sort of understand this more complex one? Yeah.
Yeah. Just say one more time what the differences between including a library in your file versus using it here.
In your C file, you're including the header, the declaration of it. This is actually including the code. It says, I need the code from that to be copied into this driver. That's what it says. And that's just the way the bookkeeping is done with the compiler. Yeah.
So when you make a make file to submit, what's the extension?
No extension. It's just make file. Yeah. Yep.
Why do you have two OBJs? Like, why do you have two objects in your driver?
Oh, so this says that the driver depends on these things, these four things, and the header files. So these are the sub-targets. So if the sub-targets are out of date, then rebuild the driver from these sub-targets. And so it'll check the modified date on these header files and compare it to the driver, as well as these object files. And if it needs to rebuild an object file, then it has to trickle down to the next, the rule that would build that object file. Yeah.
So why is there the objects again when the line just there right there?
So this is the rule to compile it. And so in order to compile the final binary called driver, it's going to paste together all the object files that consist. Yeah, so then this is included because you need those .o files. Because what it's going to do, the compiler in the final linking step will say all the libraries from the math library, all the object code that you've written, they all get pasted together and then put into the driver is the syntax of that. That's a good question, because I didn't explain that at all. All right. Your make files are going to be more like that. But the reason I'm introducing this to you is because eventually, if you're programming in C, you'll see the larger make files. And so that's why. All right. The other thing that you might need for your program is using a debugger. Did Warren a little bit with the debugger? Not much? All right, so here is our walkthrough of the debugger. And the debugger is one of these things you just need your repetitions on. Like, it's hard to learn how to use it without like really banging your head on the debugger for a while. So there are, later on in this class, I have this little CTF where we give you practice in the debugger. We give you some levels to get yourself comfortable with navigating a debugger. What I want you to get out of this particular walkthrough is the kinds of things you can do with the debugger, so that when it comes to the case, it's like, I need to know exactly when that variable changes in my program, because when it changes is when it gets corrupted. I want you to be able to say, oh, I remember in class, he set a watch point on that variable, and the debugger stopped when it was about to get modified. That's what I want you to get out of it. And then the mechanics of the commands to actually implement that, you can look that up, or you can replay this lecture. So this is the debugger. Debuggers allow you to examine and control program execution. If you want to use the debugger to debug your program, you would typically compile it with the -G flag. Now you can bring up binaries that haven't been compiled with a -G flag up in the debugger. It's just that you don't get any of the symbols, like the variable names or the source code listings, to help you debug that program. So that's the reason why you would include the -G option. I'm gonna go through the GNU debugger, but the functionality that I'm going to give you is common across any debugger that you would come across. So again, don't get too concerned about the specifics. Think about more conceptually what is being done here. I'm going to show you GDB with the -TUI option set. So this is sort of a text-based graphical interface to the debugger, which I like because it works everywhere, and you don't need some fancy X Windows terminal to actually get an app running. If you are on the Linux Lab machines, I think there is DDD installed, which is a graphical, it's a GUI that's built on top of the GDB. And then there are other debuggers that are out there. For example, in most integrated development environments, they have a debugger built in, so you can use one of those as well. Okay, so what are typical commands in GDB and in any debugger? Well, the easiest one is run, starts the program. Step, which executes until a different source line is reached. So you can think of that as just one more step in your program. Next is, it will execute until the next source line is reached. That is a bigger hop because, for example, if you are pointing at a function call, if you do step, you will step into that function call. If you do next, you'll execute that function call, return, and break on the line after that function call. And I'll show you a demo of this, a walkthrough of this at the end. So those are the two ways of single stepping through your program. There's the continue, which resumes the program execution until either it finishes or until you get a breakpoint hit or a signal received. Break says you set a breakpoint at a specific line of your code. If you know something is sort of hairy, at a particular spot in your code, you can set a breakpoint there, and then you can print out the different variables that are around that line of code to see if, in fact, you can sanity check the variables in your program at that point. Similarly, you can use delete to delete specific breakpoints that you've set previously. There is the watch instruction, which says, rather than break on a specific instruction, I want you to break whenever a variable gets accessed or changed. So it's a data watch point. This comes in really handy. For example, if you ever get a segmentation fault, which you will, like if you can manage the first program without a segmentation fault, I give you a round of applause. But if you get a segmentation fault and you're like, well, how do I debug that? Well, one of the things you can do is say, hey, I have some pointers in my program. I'm going to set watch points on these pointers. And I know I've initialized these pointers to point to the right things at the beginning. Something is corrupting that pointer. It's making it go point to somewhere else. I'll set a watch point there, run my program in a debugger, and then it'll show me the telltale instruction, hopefully, that's caused that corruption. Okay. When you have broken in the debugger, you can navigate the state of your program. And you can use the print instructions to print all sorts of things. Like, so if I'm broken, I can print the argc. I can get access to the variable names as they've been declared in my program. And that's by using the -G flag, you are able to do stuff like print argv and print argc in that program's context. We'll get to this later, but you can actually get the contents of the CPU. So as your program is executing, the CPU state, the registers are being updated underneath, and you can get access to these registers. For example, this is the stack pointer register, which we'll get familiar with later. If I want to print that and see what the stack pointer is pointing to, I can just do a print $RSP, and then I can get the address that it's pointing to and then dump the memory that's there to figure out, okay, the stack is what it needs to be, or it somehow got messed up. If I have a memory location and I want to print the hexadecimal representation of whatever's there, I can do a print /x of that memory location. So /x says I want this thing in hexadecimal. I could actually invoke a printf with a format string. So if I want to interpret argv as a pointer to a string, I can just do a printf %s and then give it argv of 0. Another command that you'll be using later on is to examine x, something in memory. So this is typically, the argument is a memory location. So if I want to examine the string, so /s says string, examine the string that RAX points to. So this is another register. So say I loaded a pointer to a string in RAX, I can just print what that string is by doing that. If I want to print the 32 words at this address, then and I want it in hexadecimal, then I can say examine 32 words in hexadecimal at that address. And you can just pass the examine flag, or the examine command, the different flags that you need to format the output that you want. All right. List displays the source code of your program, so you need to figure out where you're going to set breakpoints. So it would be helpful to list the program, and you get program line numbers, and then you can say break at that line number. I'll show you that in a second. Disassemble function gives you the x86 machine code for that C code that you're trying to analyze. So this will definitely be something you'll use in Chapter 3, and less so right now for this program. But I figured I'd just go through all of GDB right now rather than doing a GDB for C programs and then a GDB for reversing binaries. So that's why that's all interleaved. Another useful command is where. So where produces a stack trace, which is a chain of function calls that led you to your current location in the program. So you can have main, which calls foo, and foo, which calls bar calls printf, and say you crash in printf. In the debugger, you say, oh, segmentation fault. When the program aborts in printf, if you type where, it'll give you that call chain. And then you'll know, hey, it's my function, what was the last function I said, bar? Yeah, there's something going on in bar that's calling printf and calling the thing to crash, and then you can narrow where you are. So that's where or backtrace will get you. If you are trying to debug your program, if you crashed in printf and you wanted to figure out what variables in main were, you're in the wrong context because the variables are out of scope in printf, right? You don't have access to the local variables of bar or the local variables of foo or the local variables of main. But in the debugger, everything's open to you. You just have to say, well, go up a frame and give me the variables there, or go up another frame context and give me the variables there. That's what up and down do in the debugger. It's like, I don't want the current context to be printf. I'm going to go up a stack frame to bar, and then I'll print up, and then all of the variable names in bar come into my context, and I can print those out using the variable names in those functions. Info is a general purpose command that gets you information on either breakpoints or the machine registers. and then quit is exiting the debugger. So that is pretty dry. What I want to do, one last thing. GDB TUI is, so dash TUI is what that should say. This is a option sent to GDB to get that curses interface to the debugger. If you invoke GDB and you want to invoke the TUI from GDB, then you could also do layout split. And you can say layout split, layout ASM if you want to see the assembly code, layout registers if you want to see the registers, and you can pretty much regenerate what GDB-TUI gives you. I actually have aliased GDB on my computer to be GDB-TUI, so I don't really use these commands, but you may not want to. And then to get the curses interface, this is all you would have to do inside of GDB. Okay, so this is dry. All these commands are dry unless you actually use them. So I have this example program and an example script through the debugger, which is what follows, that I'm going to show you the use of the different commands with. So this program is pretty simple. So we'll start with main. It's got a integer x, which is uninitialized initially, and then it sets it to 30, calls subroutine 2 with that parameter. So that just prints 30. And then sets x to 90, and then prints 90. Calls subroutine 3, which does some funky sprintf. That you don't have to worry about. And then continues, prints that out and returns. And so what I'm going to show you is with the debugger, poking at different parts of this, setting breakpoints, etc. So I will bring up my Ubuntu box. Here's my make file. So I have GDBX, scanf, and scanf bounded, and these are the compiler commands to build those things. So with GDBX, I have the -G option set. The other thing I have set here, which might be useful for you to set, is -O0. This means don't turn on any optimizations. And the reason why I would do this is because the compiler will look at your code and say, you know what, it's going to be more efficient if I shuffle this code around. It'll give you the same result, but I'll compile it to make it go really fast if you turn all the optimizations on. That's great for performance, but it's terrible when you're trying to debug a problem in your program. So you want the order in which you wrote the code to be the order in which the compiler emits the code or executes the code. Otherwise, yeah, your brain will explode trying to debug your program, especially if the bug is in that area that it reordered. So I set it with the -0 flag, 0 optimizations, or level 0 optimizations. I set the object file to this binary GDBX, and then that's the source code. All right, so I will start with GDB-TUI GDB exec. And let me see if I can put on the side. Let me put the Alright, so the code is there. The code might be here too. Alright, there's the code. Alright, so here is my code. And this is because I used the -G option. It will show up source code on this. One of the things that you might want to do is send the program command line parameters. So the way you do that in GDB is to say, I'm going to set my arguments to be, let's say, A, B, C, D. And then the list command, which I talked about, says, give me a listing of lines 1 to 22. And then that lists all of this. Say I want to break at this at the entry to main. So I'll do a break on main. And you can see on the left, it set a breakpoint here, right after the initialization. So this is really the first instruction in main. So that's why it set a breakpoint right here. So that's where that B+ is. I can do a break on subroutine, which is up here. So I can use that symbol, sub, because I've used the -G options and the symbols are there, so there's where that is. I can do a breakpoint at, where else do I want the breakpoint? Line 6, which is this one. If I do an info of BR, you'll see that these breakpoints are at these line numbers. Okay. I'm going to run the program. And you can see it broke right here on this very first instruction of main. I can print argc, 5 arguments, because I have A, B, C, and D plus the GDBX. I can print the, let's see here, print the address of argv. So this is a pointer to a bunch of pointers. So this is on the stack, somewhere on the stack, this argv pointer. I can actually print what argv of 0 is, just like in that program before. So that's the name of the binary. I can print argv of 1, which is A, and 2, which is B. I can print X, and X is 0 right now because it's uninitialized. So if I execute the instruction, so I'll go next, and then I print X, it's now 30. I can print this in hexadecimal with the /x flag, and that's hex 1e, which is 30. I can print the address of X, if I wanted to, and that's on the stack. What else is here? I can examine the word that's at the address of X. So this is the examine statement for examining memory locations, and I say I'm going to examine the address, what's at the address of X, and this should be hex 1e. So that's there. All right, I am going to go next, and when I do next, rather than entering into sub2, it will execute sub2 in its entirety and get you to X is equal to 90, which is what it does. So now I'm here, X is 90, or right before X is 90. Let's see, I can step. Well, I can print X, which is still going to be 30, and then I can step, and it's now 90. Now, rather than doing a next over sub2, if I step, it's going to go enter sub2. So I'm going to enter into sub2 rather than executing it in its entirety. And so now I'm on this printf because I stepped into the function. Okay. I can type where. So I am in sub2 in main. So that's what I'm talking about with the backtrace. And if I try and print X here, there's no symbol in the current context. But I can go up a frame. And so I'm in frame number 0. I can go up to frame number 1. And now I'm in main. And then I can print X again. So print 90 is there. I can go back down. And then I'll continue. And it hits this breakpoint again. Sorry, the curses interface sometimes gets confused, and you have to do a Control-L to refresh the screen. Or you can type refresh on the command line itself, and it'll refresh the screen. So it hit the breakpoint in sub, and then if I continue, it'll do a printf and return. Oh, no, there's a breakpoint at 6, and then I can continue and return. Okay, so I have these 3 breakpoints here. I'm going to delete number 2, delete number 3, do an info BR. So now I have the 1 breakpoint in main, and I'm going to rerun this program. And I'm back here, and I'll do a step and print X. So now this is 30. Now I want to set a watch point. I know X is a sensitive number, And so I want to make sure, I want the debugger to break as soon as it changes. So now I'm going to do a watch on variable x. And this sets a hardware watch point. So the way it's implemented is that the CPU has these hardware registers that say, if there is an address over the address bus that matches this pattern, I'm going to send an interrupt. I'm going to throw an exception. And this is how this particular watch point is implemented, in conjunction with the hardware underneath that's got these hardware registers to watch the memory addresses going back and forth. So if I continue here, it should break when I set x to 90. And that's where it does. And so you can see the old value is 30, the new value is 90, and it broke right after that x equal 90 instruction was executed.
What does continue do? So continue goes until you hit a breakpoint?
Yeah. So that is pretty much all the functionality I think you need to navigate around in the debugger. Continue, and I think that's it. Hang on a second. Are there any questions about GDB? Hopefully you will get some use out of it for your program. That's DDD. And that's it for today. Are there any questions about the program? So I think you have, now after this class, you have everything you need to write that program, that first program. If there are any issues, post it on the discussion board. Let me know. So over the weekend, I would imagine people are going to be hopefully getting a good crack at it. And then Tuesday, if you have any last minute questions, let me know. All right.